This is a review video on empirical and molecular formulas. So we'll start with empirical first. Definition of an empirical formula is the lowest whole number ratio of elements in a compound. So we'll go over a few examples. What is an empirical formula? What is not an empirical formula? So, for example, H2O. Okay, so H2O is a ratio of 2 hydrogens for every 1 oxygen. So the ratio is 2 to 1. That ratio cannot be reduced and still have whole numbers. So H2O is in fact an empirical formula. It meets this criteria, lowest whole number ratio. Something else that would be an empirical formula, how about carbon monoxide? Okay, so this ratio is a 1 to 1, and of course that can't be reduced, so this is also an empirical formula. How about Al2O3, aluminum oxide? In this case, the ratio is 2 to 3. And 2 to 3 can also not be reduced and still have whole numbers, so this is also an empirical formula. But then something like this, which is the formula for glucose, the ratio is 6 to 12 to 6, which we all know can be reduced down to 1 to 2 to 1. So the formula for glucose is in fact C6H12O6, but that is not an empirical formula. So it does not meet the criteria for an empirical, and it will be referred to as a molecular formula, which is what we're gonna talk about in a little bit. So that's how you tell an empirical formula. It's pretty easy. Calculating empirical formulas, though, is a little bit trickier. It's just a series of steps, and so we'll solve probably 2 of them. Okay, so most of the time when you encounter an empirical formula problem, it's given in percentages. So you'll see something like this: calculate the empirical formula of a substance that's 10.4% carbon, 27.8% sulfur, and 61.7% chlorine is this one. So, okay, so the percentages right away tend to throw students off, but if we just make an assumption that we have 100 grams of a substance, okay, so we have 100 grams of this mystery substance, and 10.4% of it is carbon, then that would mean 10.4 grams of it is carbon. So in our head, we just take our percentages and change them to grams. So I'm just gonna erase these and take them right into grams. Now, sometimes you might just be given grams and then you don't even have to think about that step. But if you're given percentages, you can just change them into grams and go from there. So the goal here, of course, is to find the subscripts in this formula, which I'll denote with X, Y, and Z. And again, since it's empirical, it's going to be the smallest whole number ratio. So I'm looking for X, Y, and Z. Now, the important thing is that X, Y, and Z, in this case, these are mole ratios, okay? They're mole relationships. So because I'm given grams here, I need to take those grams and change to moles. So that's my first step, and that is using molar mass, of course. So grams go to moles. Using the molar mass on the table, sulfur's is 32. Oh, that was carbon. I'm sorry, I thought it was CO. Carbon's is 12. And chlorine's is 35. Okay, so here we go. My grams cancel out. I need to do a little bit of math, and I will have my moles. Now in this step, be careful not to round too much. So just take it to several sig figs. And my last one, 1.763. So these are all moles, okay? But you'll notice that when you do an empirical formula calculation, the mole numbers that you get are always, I often refer to them as being kind of ugly, meaning they don't look like the numbers that you would substitute in here for X, Y, and Z to get a formula. So we have to look at the ratio between these, and the way we do that is we take the smallest mole number and divide the other ones by that. So in this case, these two are pretty much the same, but this is the smaller one. So you're going to take that and divide the other ones by that number, and that's going to give you those, for lack of a better word, those pretty whole numbers that would lead us to our empirical formula. So this is obviously going to give me 1. This obviously also gives me 1, and the bottom one is going to give me 2. It actually gives me like 2.02 or something like that, but that's close enough that here's my mole relationship, or my mole ratio. So it's a 1 to 1 to 2, which means my empirical formula would be C1, which I don't have to write, S1, which I don't have to write, Cl2, and there is my empirical formula answer. Notice 1 to 1 to 2 cannot be reduced, so it is an empirical formula. So that's that one. Let's do another one. They can get slightly harder, and so I picked the next one. It's just a little bit harder, so it's a good one to do an example with. All right, this one said 62.1% carbon, I can't read my own handwriting, 5.2% hydrogen, 12.1% nitrogen, and the rest was oxygen. Okay, so in this case, I have a 4 element formula. So C, I guess X, Y, and Z won't work. So C, W, H, X, N, Y, and O, Z. And so I'm looking for my 4 letters up there. Again, they're mole numbers, so I'm going to have to change these values into moles. First of all, you'll notice that you weren't given the percentage of oxygen, but if it's percentage, it's of course all based on 100. So whatever this is minus 100 has to be the percent of oxygen. So let me do that real quick. So 100, this was 79.4, so 100 minus 79.4 has to be the percent of oxygen, which in this case is 20.6. So again, given percentages, just make the assumption that these are all grams, and then I can go from there. Biggest thing you have to remember in empirical formula is you have to change them into moles, because these are mole relationships, and so we'll do that by using our molar mass. So let's see, O is 16 grams, 14 grams, 1 gram, 12 grams for quickness here. I just left out the 1 mole on top. I shouldn't, but I did. Okay, now I do my math. Again, being careful not to round too much. This, of course, is just going to give me 5.2. This is this, and then my last one, 1.288. Okay, so these are all moles. I guess I can attach that on there. Again, these numbers do not look like numbers that we would plug into my letters up here to write a formula, so I need to divide by the smallest one. This one's obviously the smallest, so I'm going to divide everything by that. And you do that every single time in every empirical formula problem. So I go through now, and I'm hoping that I get some whole numbers out of this. So this gives me 5.98, which is close enough to 6, which is probably going to be the second one also, because they were so similar. Yeah, so this gives me 6.01, which again is close enough to 6. This one, of course, gives me 1, and then my bottom one gives me 1.49, which is truly 1.5. So I'll call it 1.5. And this is where students get a little bit confused and they're not sure what to do. So this is a great example. Okay, so when you encounter something like this, a lot of students just want to round this up to 2 and call it done, because we've always been taught that a 0.5 rounds to 2. But in this case, I cannot do that, because this relationship is 6 to 6 to 1 to 1.5, not 6 to 6 to 1 to 2. So that's totally different, and I'm not allowed to do that. I'm also not allowed to round it down. So I have to get this number to be a whole number by doing something to it, which means I need to multiply it by something, and I can't multiply it by 1, but if I multiply it by 2, that would give me a 3, and then everything is good. But if I multiply this by 2, I have to do the same thing to these other ones. So all of these get multiplied by 2, which is going to give me 12, 12, 2, and 3. Notice 12 to 12 to 2 to 3 cannot be reduced, and so my empirical formula is C12, H12, N2O3. And there it is, my empirical formula for this. All right, last thing we have to talk about is a molecular formula. and this is the easy one. So empirical is just a series of steps to perform those calculations, but molecular is much easier. So the definition for molecular is it can be equal to or a whole number multiple of the empirical. And I'll tell you what I mean by that. So just a few minutes ago when we encountered glucose, we learned that glucose has a formula of C6H12O6, which is in fact a molecular formula. So if you think about it, I can drop this down to 1 to 2 to 1 and get CH2O, which is in fact the empirical formula of glucose. Okay, so if you look at this, in this case, the formula for glucose is 6 times bigger than the empirical formula. And so that's what it means here, that it can be a whole number multiple. So in this case, glucose is 6 times bigger than its empirical. Sometimes they can be 2 times bigger or 4 times bigger, or even 7 times bigger. Sometimes though, the molecular can actually be equal to the empirical formula. So that's kind of interesting, and we'll see that later. Okay, so a molecular calculation is so much simpler than an empirical, but you have to know 2 things. So this is super important. To find a molecular, you must have, I missed a word. You must have the empirical. Okay, so we've already had a discussion on how to find that. And then 2, you must have the molar mass of the molecular. Okay, so this is very important. It's something that you need to remember. To find a molecular formula, you have to have the empirical formula and you have to have the molar mass. So if you don't have an empirical formula, you obviously have to find an empirical first before you can talk about figuring out a molecular formula. So we'll do a quick example and we'll be done. Okay, so the problem says a formula, or the empirical formula of a substance is CH2. Again, notice 1 to 2 can't be reduced. And it has a molar mass, I'll call MM, of 84. And it wants to know the molecular. Okay, so we just learned a molecular is either equal to or is a whole number multiple of the empirical. So technically the molecular formula could be this. It could be twice as big as that. It could be 4 times as big as that. It could be 9 times as big as that. So how do we solve it? So it's actually quite simple. If we know the molecular formula's molar mass, all we do is do the empirical formula's molar mass, which would be, let's see, 12 plus 2, right? So 14. And then we do a simple comparison of the empirical molar mass to the molecular molar mass. If you can't see that in your head, you just divide the 2. So you take 84 divided by 14. And you get 6, okay, which means that the molecular formula must be 6 times bigger, okay, or 6 times more massive than the empirical. So I just multiply the empirical formula by 6. That's it, which gives me C6H12. And if you want to check, you can check your molar mass by doing 6 times 12 plus your 12 hydrogens, which is, of course, 84. And so this does, this matches this. It does work out. Here's your molecular formula. So molecular formula found very simply by taking the empirical formula's molar mass and comparing it to what you were given in the problem, and then figuring out how many times bigger the molecular is. So that is a quick review on empirical and molecular formulas.